Okay, so hey everybody, thanks for coming back. Yeah, this is lecture two of our series on algebraic geometry. And we'll just be kind of picking up from last lecture. I wasn't super happy with how some of the things came across. Um, and so we're going to refine it some. And I gave this colloquium talk that some of you were there for um, the other day. Talked about projective space, and I liked my explanation from that better than what I gave last time. So I'm going to give that explanation of projective space, and I think that that will maybe make some things click. So the idea generally is that algebraic geometry kind of wants to study things about like general mathematical objects cut out by zero sets of polynomial equations. And so in the real plane, if we take some polynomial like so, well, we can get a line through this equation, and we can express their intersection as the zero set of some polynomial, right? Well, this is nice. You get, one intersection, two intersections, three intersections, four, and five. And then in terms of the number of bumps that we have one bump, two bump, three bump, four bump. And assuming it's going to say that this is monotonically decreasing that way and monotonically increasing this way, right? Yes.
So you say that the zero set is some polynomials, you mean like the difference of those two polynomials, like that zero set, or
Rather, it would be that if the first one is f and the second one is g, then we would take f of x minus g of x equals 0. Okay. Yeah. Or like say
Well, that's not enough.
that is not enough, yeah. But this would be like kind of how you would start to express that. Yeah. But kind of the problem is that, well, this line is very specific. There is an exact interval and range of slopes that we can have for this line such that we actually do get all five of these intersections. And so if we move this line down at all or change the slope at all, right? Maybe we get the same intersection, but maybe like we don't get the other four. Similarly, if we change the intercept, maybe we get this intersection, or just two of them, or just three of them, or something weird. So Poncelet came up with the idea that this is bad, and that instead of thinking of square roots of numbers as like this geometric construction with the Pythagorean theorem, that maybe we actually kind of need there to be a consistent way to measure intersection multiplicities, and intersection numbers of one curve with another curve. So what he came up with was that the complex number should do this because we can express the intersection of a line with a curve over the complex numbers by the fundamental theorem of algebra. This polynomial will have as many roots as the degree of that polynomial. Well, this is great, but there's this thing called the Galois correspondence of roots that says that basically if you have a polynomial with real valued coefficients, then if it has one complex root, it will have a second one. Namely, it'll be plus or minus square root of negative whatever. So like for example, x squared plus 1 equals 0 has roots plus or minus square root negative, right? Okay, well, this is fine and dandy, except we can construct a 6-degree polynomial intersecting a real line in one place, meaning that, according to Poncelet, the other 5 roots should be in the complex plane, off the real line. And the problem with this is, of course, that we get 4 roots in the complex plane and 1 division by 0. So Poncelet said, okay, well, now we need something that makes this consistent where that thing at infinity, that division by 0, like actually exists, and we count it as an intersection point. And so this is where the idea of, well, projective space should be the space where parallel lines meet at infinity comes from, is, well, to meet at infinity, we have to think of it as, well, infinity is the place where if it doesn't intersect anywhere else, it should intersect here. Okay, so kind of the example that I came up with No, I didn't come up with this. John Webb came up with the example. And then Dr. Field and I worked on this a little bit the other day because Dr. Webb had proposed that certain points satisfied these equations. Turned out that they did, and it gave actually a really interesting example that I thought I would share with you. So taking two parabolas in the plane, like so, take y equals x squared, and y equals 2 minus x squared. We get intersections at 1, 1, and minus 1, 1. But kind of taking this idea, we should be able to move things around in the plane to get them to intersect, quote unquote, generically in terms of what we want the intersection multiplicity to be. If we flip one of these on the side, we see that we can construct this setup where we get 4 points of intersection. So we can kind of intuit that, well, this is a degree 2 polynomial, and this is a degree 2 polynomial. We maybe want them to intersect in the product of the degrees. Then maybe we want projective space to be the space where, given two curves of degree d and e respectively, they intersect d times e many times. And so what we'll do is we will projectivize these two curves, and then we'll show that they intersect in 4 places, or at least with multiplicity 4. So again,
what happens with like surfaces?
Intersection multiplicity for surfaces is complicated. So ask me about that after. We can talk about that after. But it gets more complicated. The idea is that you really do need schemes. And so you define things in terms of the dimension of local rings. And that'll be how we define eventually the multiplicity of two general varieties at a point or along a line or along a subvariety. But that's like usually much later because you need things like divisors. So anyway, so let's projectivize. So again, we're gonna do the thing we did last week. Send x to x over z, y to y over z. We'll get y over z is equal to x squared over z squared, or yz is equal to x squared. And then we'll also get y over z is equal to 2 minus x squared over z squared. And we get that yz is equal to 2z squared minus x squared. Matching these up, we can eliminate the yz and yz term and get that x squared is equal to 2z squared minus x squared. Taking some liberties, moving this over, we get 2x squared minus 2z squared equals 0. Is the equation defining our projective intersections. Or is, yeah, it's one equation. And so we want to verify that our original, so again, we know that 1, 1 and minus 1, 1 take the projective coordinate form minus 1, 1, 1, since we're setting z to be equal to, right? So x is just x if we set z equal to 1, because it's x equals x under 1. Similarly, we have 1, 1, 1. But now we want to do something on the line at infinity, and so we're going to pick something, something, and 0, and then I'm going to claim that there's actually no fourth point and that there's multiplicity 2 at this point. And then I'm going to explain what that means, and we're going to work out why this makes sense. Yes?
Are you subtracting one? Like, are you subtracting those two matrices?
So these are matrices. These are just coordinates.
Coordinates?
Yeah, so we mean that these are projective coordinates, and we distinguish these from affine coordinates. Like we could write this as 1, 1, 1, but then you wouldn't really be able to tell whether or not this is in affine 3 space or like C3 versus being in P2.
Do you have to do any type of arithmetic, or is that not interrelated? Like with this particular.
Yeah, no, not really related. Yeah. Yeah. No, I get it. It's kind of like confusing because it looks like it should maybe be like a row vector or something. Yeah. No, it's not. So if we use matrices at all, I'll say like matrix something rather. Okay, so picking out this zero condition, well, we get that if z squared is 0, or rather if z is 0, then z squared is 0, then we get 2 squared equals 0. 2 is not 0, so x is 0. And then it actually doesn't matter what y is in this case, and so we just need to pick a y so that the original equations are satisfied, right? So namely, yeah, namely, if we plug in 0 and 0 for both of these, then we can pick y to be 1 because it's multiplied by 0. And so this will span a line at infinity of solutions, and we just need to figure out what the multiplicity is along this line of the intersection of these two equations. So the way we kind of want to think of intersection multiplicity is when we intersect these two things, how many tangent vectors do we need to define the space of tangent lines or tangent O-dimensional surfaces at this point? And so kind of the general way to do this is I'm just going to make some mild alterations. Get these equal to 0. Going to call this first one F and the second one G. And then the idea is that we should consider the partial derivatives, the first partial derivatives, with respect to x, y, and z of f and g, and then we should plug in this point, right? And to be clear, the reason why we're doing this is because the only thing that we could possibly get out of x at z equals 0 is 0. And so picking any other like coefficient, like 0 to 0, we defined all of our projective points to be equivalence classes of lines to the origin under this multiplicative equivalence class, where we say that lambda times all of these things is equal to this thing. So that's just one point, right? So this is what leads us to believe that we should do this in the first place. Okay. So partial of f with respect to x is going to be minus 2x. Partial of g with respect to x is going to be 2x. Partial of f with respect to y is going to be equal to z. Partial of g with respect to y is going to be equal to z. And then I'm going to do this down so that we don't lose this on the video. But partial f with respect to z is y. And then the partial of g with respect to z is also y. Well, now if we plug in 0, 1, 0 for each of these points, we get that this is 0, and this is 0, and this is 0, and this is 0, and this is 1, and this is 1. So, yeah.
Sorry.
You're good.
So all the y values are 1, and all that things that aren't y values are all zeros.
Yeah, exactly. And so basically, if we express this as a matrix, if we put partial f with respect to x, and f with respect to y, and f with respect to z, gx, gy, and gz, and we evaluate this at the point, then this matrix is going to have rank 1, right? Meaning that its codimension is 2, or 3 minus 1. And we're going to define the dimension of the tangent space at a point to be the codimension of this matrix. So the multiplicity at 0, 1, 0 is 2. So we get out of this kind of that projective space is the space where, given two curves of degree d and e, they intersect d times e many times, including multiplicity. And so this is called topological Bézou's theorem, and it's because we're just considering curves in the plane. Okay, so this is really what I want you to think of projective space as, is like it's the place where things intersect the right number of times given the equations defining them. And beyond that, we can do some really technical, cool stuff with it. But when it comes down to it, that's like our geometric intuition for it. And when we talk about projective varieties, I think it'll make sense to talk about affine varieties first and carry that intuition over. So. Okay, so now we're actually going to talk about affine varieties. And so this is something that honestly probably should have started with last time, but this is my first time really teaching like something like this, so it's a learning process for me. Okay, so I've written up a bunch of like colloquialisms that I like to use on the sideboard. And they're things that like are just common words in algebraic geometry. But if I ever say something that isn't on the board, please ask me to add it to the board immediately, because I guarantee you, if you don't know the word, somebody else in the room doesn't know the word, and that's not a good thing. And then also, yeah, if you get confused by something, feel free to ask me, but also feel free to see if it's on the board as well. Okay, so I just want you for now to consider Cn, or affine n space is kind of what we'll call it. So we defined affine n space to be like a vector space over C, or really some algebraically closed field K, meaning that the roots of all polynomials with coefficients in K are in the base field K. That's what we mean when we say algebraically closed. We're going to kind of want to think of affine space as like a vector space over C, but it doesn't preserve anything under linear transformation. And so what I mean by this is like if we have a circle up to affine equivalence, any linear transformation of the equation of a circle is still a circle. So we would characterize this instead of, x squared plus y squared is equal to r. This is really x plus a squared plus y plus b squared equals r plus c. And so this is kind of the condition that we're placed on affine space. And in this way, like we're not preserving magnitude, we're not preserving angles, but we are preserving the equations that cut out these general objects. And so the focus becomes less like what we can see in the plane and more about the equations that cut out these things that we care about for some reason. Okay, so kind of another foundational definition is the zero set of some polynomials. So given f1 through fs in some algebraically closed field K over x1 to xn, we'll define the zero locus for the zero set or the affine variety, all equivalent words, of f1 through fs to be the set of points in affine n space such that fi of p is equal to 0 for all I. And so this is called, again, zero locus slash set slash affine variety. And then a set y contained in an is called an algebraic set. If there exist polynomials f1 through fs with the zero set of f1 through fs equal to y. it's kind of at this point that we want to introduce this notion called the Zariski topology. And so I know that we have some people in here and some people watching this who haven't taken 435 or maybe 410 as well. And so I think it's kind of useful to talk about what a topology is. I don't have this in the notes though. So in general, given a set, a topology is a set of subsets of the set that we're going to call open sets. And these open sets are kind of related to some conditions. So namely, so given a set X, then a topology tau on X, if and only if X and the empty set are both open tau. So this is the thing I like to use for open. So it's just a subset with a circle over it. And then arbitrary unions of open sets are open. And then finite intersections of open sets are open. Probably the best example of this that everybody in the room is familiar with. Yes.
Subset with the circle,
Yeah.
not element though?
Oh, yeah. I mean, yeah, you're right. Yeah. So this should be a subset with a circle on it of X or every set comma X or tau. Yeah. This is useful, like if we don't name the topology something, and we just say put a topological space on X, which is what we're going to do most of the time. This notation lets us just say that like it's open in the topology on X. By and large, we're going to use this thing called the Zariski topology. It's never going to change. And so instead of designating it as like some fancy character, we're just going to say like is open in the set. So yeah, sorry, that is unconventional. It's just kind of a time saver. Okay, but the topology that we're all really familiar with is the real line. So like in high school calculus, you end up seeing that like, oh, we'll call these things open sets, like from A, comma B, right? Well, pick A, pick B, pick C and D. Pretty clearly, their intersection is also an open set, CB, and their union is also an open set, AD. I mean, it's less obvious that the empty set is open and all of R is open, but if we define it to be that way, you know, kind of nice. So yeah, this should be like kind of your grounding example for a topology. It's the real line chunked up by open intervals. And then similarly, we say that something like a subset of our set is closed if it's the complement of an open set. So a closed set is just the complement of an open set. Okay. So now what we want to do is we want to define this thing called the Zariski topology. And so this is kind of like how people did algebraic geometry for a really long time was with Zariski. So in the Zariski topology, open sets, or rather, no, closed sets, we'll start with that, are algebraic sets. AKA sets who happen to be the zero locus of some polynômials. And then open sets are the complement of closed sets. And I'll just kind of provide a supplementary definition. So a distinguished open set DF is typically the complement of F with an X, or if it's some other ambient space, like whatever our ambient space is, X set minus your set. This allows us to consider open sets of varieties. Okay, so kind of some ways of yeah, let's not get there. It's gonna take too long. Some people like to have the condition that varieties are irreducible, meaning there are no two other. So given a variety, which is an algebraic set, which is a closed set in the Zariski topology, there are no other two sets whose union are that variety. Harris doesn't do this because for enumerative geometry, it's kind of splitting hairs, and it makes things harder than it has to be on vectors. I'm not going to include this notion, but a lot of algebraic geometry books do. So if you like go and read through one for fun, always check that they're always going to say it in the first chapter somewhere, whether or not they assume varieties are irreducible.
What do they call them, non-irreducible?
A variety.
Or sorry, like, no,
Reducible. Oh, reducible, yeah.
say it's a reducible variety, the variety is irreducible.
Yeah. Yeah. I will say those words kind of get confusing at some point because there's a notion of like an irreducible reduced scheme. And that's a thing. It's kind of an important thing later on. We're not going to talk so much about schemes, so it doesn't matter to us. But if any of you 3, 4 take a course in algebraic geometry in grad school, you'll see schemes, and that will have these things, and those words will be confusing. So this is my disclaimer. Okay, so an affine variety is a closed set in the Zariski topology. Then a quasi-affine variety is a distinguished open set of a variety. So so definition, if X is a variety, affine or projective, then DF is a quasi whatever it is variety. So either affine or projective variety. Okay. So this is kind of our setup. This is our setup for what affine space is, what an affine variety is, and then this thing called a quasi-affine variety. In general, the varieties that we're going to talk about and we're going to use as like interesting examples are quasi-projective varieties. So if you take some projective variety and then you cut out some distinguished open set on it, that's usually what we're going to be talking about. So like last time we were talking about the rational normal curve and the twisted cubic. That's an example of a quasi-projective variety. We'll also talk about these things called Segre varieties, I think next lecture. Those are an example. Today we're kind of slated to go through some stuff in commutative algebra. And so I know Josh has taken 431. I don't think Jorge is in 431, and then I don't think anybody else has taken 431. So this is going to be some new stuff. When I say ring, what I really want you to think of is something that looks kind of like Z. And the reason why is we can add and subtract numbers in Z, and they stay in Z. So we have closure and we have inverses. Addition is an associative product. And then we also have an identity element, 0. We can multiply integers. We can't divide integers. But multiplication is associative, so it's still pretty well behaved. And we have an identity element, 1. So we'll call this a ring with unity, really, is a ring with 1 or some kind of multiplicative unit. You can learn a lot more about rings. I can send out something on the email chain for people who are interested to learn a little bit more. But really, you should take 430 and 431. Yeah.
Sorry, it. Okay, so is that abstract algebra? Like-
Yes.
Okay, so is when you're saying 430, 431?
Yeah, abstract algebra. Yeah, so abstract algebra 1, you learn about group theory. A good example of a group is Z under addition. And then a ring is like a group, but you add in the second product that doesn't have to be as well behaved.
Gotcha.
Right? It still needs to be closed, still needs to be associative. Typically, some people will assume unity, so 1. But it maybe doesn't have to have inverses. And you can kind of stratify this definition a little bit. Like for example, the integers mod 6, you can have 3 times 2 is congruent to 0. But in Z, any 2 elements are only equal to 0 when multiplied together if and only if one of them is 0. So like that's one way that you can stratify types of rings. It's a neat class. Definitely take it. Okay. Yeah, so given a ring R, and we'll just assume that it's commutative, meaning that when we multiply 2 things, A times B is equal to B times A. So given a commutative ring with unity, R, we're going to define an ideal of R. So I contained in R is called an ideal. If and only if for all A in I and B in R, A times B is I. This was a long time ago explained to me as something called sticky multiplication. I kind of like that word. You take, A in here and B out here, and it sticks to the A, and it lands at AB. Right? So sticky multiplication. And then for any 2 things, A and B, just in the ideal, A plus B should be in R. Okay. So then following this definition, we'll say that if there's like a list of ring elements that generate the ideal, i.e., if F1 through Fs in R are such that this bracket, I'll call this Langle and this Wrangle because that's what it is in LaTeX. If the linear combination of ring elements is equal to I, then we say that I is finitely generated by these things, right? So this is just like a generating set, but usually this is an ideal. Not all ideals are finitely generated. So if all of the ideals of a ring are finitely generated, we say that this ring is called Noetherian. Noetherian rings are important. There's more going on here than I'm saying. It's just kind of I'm saying this so that you see it once. But yeah, in general, we'll typically work with a Noetherian assumption. Again, if you take a class on schemes in grad school, you will both be familiar with Noetherian rings, and they won't assume that. So, okay, quotient rings. So the idea of a quotient ring is that given R and I like we had before, we'll find R mod I to be the set of A plus I, where A is in R, and rather its equivalence classes of A plus I mod I. And so the idea is that there exists some kind of like division algorithm that we can work out so that A reduces mod the things that generate I. So kind of the fast example that I'll give, and that we'll prove something about in a second, is that that R adjoint X mod X squared plus 1, the ideal X squared plus 1, is going to look like 0, 1, X, and 1 plus X. And then we're going to prove something cool about this in a second. But the idea is, okay, well, what we're saying is that that anything of the form x squared plus 1, we can take any polynomial f of x plus the ideal generator by x squared plus 1.
Do you need to use Algebraic instead of set brackets?
Where?
When you said that?
Yeah.
No, like right next to it.
This?
Yeah, because doesn't that mean that it's a set of 0?
No.
Set of 1?
Put an R in front of it or something
Yeah,
like that, so
that's
that
fair.
it looks like,
Yeah, yeah, that's true.
is that better?
Yeah.
Okay.
Yeah. Yeah, it's a good amendment. But given any polynomial f of x, then it reduces somehow by x squared plus 1 down to one of these things, right? So for example, given like x cubed plus 2x plus 1, this is equal to x times x squared plus 1 plus some remainder, so plus x plus 1. And then x plus 1 can't be divided by x squared plus 1, and so we have one of our elements. So it works out pretty nicely. Now I'm assuming like all of the coefficients here are integers, but like you can do it with real numbers and that works out perfectly fine. Okay. Really the way we get this though is we say that, and this is called the fundamental homomorphism theorem, is that if we have a morphism or like a map R to R prime with kernel K, then R mod K is isomorphic to R prime. Okay, so these are some new words for some people. So let's define them. So a homomorphism is something with a property that phi of A times phi of B is equal to phi of AB. So this is called the homomorphism property. And other than this, it behaves exactly like a function. So all of the things that you learned in like 245 or 300 still apply, but we're just adding on this property. And then the kernel is, you can think of as like the null space. So the kernel is the set of all A in the domain, so A and R, such that phi of A is 0. So then R mod K is really thinking of sending anything like larger than the kernel to 0. Yes.
Shouldn't that be the image of phi?
Yeah, it should. I'm assuming it's surjective. You're right. So let's say that this is a surjective map onto R prime. Then yeah, and this is isomorphic. And yeah, good clarification. Okay, so we take a surjection R to R prime. We're modding out by the kernel of this homomorphism. We're getting that this is the image. Well, what is this looking like? Oh yeah, isomorphic. A bijective homomorphism. Yeah. Okay, cool. All right. So
Do they know what?
City.
Oh,
yeah.
And green. Different one.
Yeah.
Yeah, it should also be, yeah. So 5A plus 5B is equal to 5. Right, yeah. So that's the okay. There we go. So now I think kind of the cool thing here is I'll say that given let f in, we'll say r over x, that's fine. Some field over x be the minimum polynomial for some root alpha in the complex numbers. So minimum means the smallest degree polynomial with alpha as a root. Then r of x mod f of x is isomorphic C, or rather R adjoint I and the fraction field of R adjoint I. Nope, not. Sorry. R adjoint, I was jumping the gun. Fraction field of R adjoint alpha. There we go. And the gun that I was jumping is that this is really C. Okay. So let's think of this way. So we're claiming that this is isomorphic to C, not just by the theorem, but we want to see something clear about this. Well, we can map this down to R 0, 1, I, and 1 plus I. So we have kind of our bases covered. We can see that this is pretty clearly a bijection. And then we just would need to show that the homomorphism property is satisfied, and this works out. But I prepared a proof of the theorem, so we're just going to prove it. It's also worth noting that C can be replaced with any field F, and then if we pick K to be some subfield of F, so F contains K as a field, then K of X mod F of X is F adjoint alpha fraction field. So this works in general. Okay, so proof. Let me look at how I'm doing on time. This is like the second last thing. Oh yeah, pretty good. All right. So we're gonna define an evaluation map. And I'm gonna call this capital phi. So phi from K of X to K. No, K of X to F. So again, think Q over X to C. That sends a polynomial f of X to its evaluation f of alpha. Well, we're sending anything that's in K to itself. And then we're sending anything, we're sending constant maps to themselves. So constants go to themselves. So anything like 1 clearly maps over to 1. Any scalar multiple of 1 by K maps to 1. So K is fixed under phi. And then the image of phi should be, oh, right, sorry. We're also sending X to alpha. Yeah, that's the important one, right? So we have, this gives us K, and this gives us K alpha, right? Similarly, 1 over X gives us 1 over alpha. So then the image of this map is exactly K adjoint alpha. And this is given because alpha is the root of a polynomial over K. So then we want to show that the kernel, and sorry, this is the wrong phi. We want to show that the kernel of phi is exactly the ideal generated by f of x, right? And really what we're saying is that any other polynomial that goes to 0 should be a multiple of f of x. But this is exactly true because this is the minimal polynomial for alpha. So anything else that goes to 0 or vanishes on, this should probably be one of my dictionary words. I say vanish, evaluates to 0. At alpha must be a scalar multiple of f, or a polynomial multiple of f. Any polynomial multiple of f is in the ideal generated by f. And so the kernel of phi is exactly the ideal f of x. Okay. So then this thing is, we have a map from k over x to f with kernel f of x by the first homomorphism theorem. K of x mod the kernel is isomorphic to f. And so the theorem is proved. I'm not writing all of it because I don't like squatting down. I'm not lazy, I swear. So all of this is like the start of kind of abstract algebra 2. We're going to dive into some stuff called commutative algebra now. And this deals with like actual algebraic geometry as opposed to just abstract algebra. Okay. So given x with an, a variety, affine or quasi-affine, we'll define the ideal of the variety to be the set of f in whatever our base field and polynomial ring is, such that f is 0 on all of x. So the ideal of a variety is the ideal generated by all of the polynomials vanishing entirely on it. Now you can verify that this is an ideal on your own. If you haven't done something like this before, I'd suggest doing it. But if you've done something like this, it makes sense. We'll define this thing called the coordinate ring. Of the variety. And so we'll call this A of x. And this will just be our base space mod the ideal of the variety. So what this is this is the ring of functions not vanishing on all of the variety up to some equivalence class where they differ by multiplying basically by 1. And what this 1 is it's some polynomial that vanishes on x divided by some polynomial vanishing on x. We're going to generalize this to something called a regular function. And it turns out that regular functions are like one of the major focuses of maps between varieties. And that's where we'll start next lectures, talking about these things called regular maps or morphisms of varieties. It gives us a way to relate things. So let U be open, Zariski open rather, in our variety be any set that's open, and let P in this open set be any point. We say that a function f on U is regular at P if there exists an open set V in U with F restricted to V is equal to G over H, where G and H are in a polynomial ring, and H of P is non-zero. And then kind of more generally, we say that F is regular on U if for all P in U, F is regular P. Just abbreviate. So kind of the way to think of this is this is a specification, the coordinate ring is a specification of our ring of regular functions on all of our Zariski open subsets of a variety. So given some variety, X, if we can carve out some open subset U, we pick a point P, and then we take some Zariski open thing going on here as a subvariety. If there's some rational form G over H that generalizes across V to have this non-zero denominator at P for all of the P in V, then this is regular. If for every open cover of U exactly contained within U, we get this condition, then it's regular on U. And if for every open covering of our variety, this is true, we get all of X. And the phenomenon that I kind of want you to be thinking about with this is a notion of gluability of these functions. So the general thing that we want is on a variety, we want to be able to cover it with these open sets. We want to be able to transition, like snap functions onto each other, kind of like Legos, where we snap things together in terms of these G over H's and whether or not they agree on intersections of these neighborhoods V. And the general idea is that we are exactly classifying certain types of vanishing sets, and that the smallest such vanishing set should be the coordinate ring of all of X, because it has to satisfy this condition for every single point in X. So this is the smaller one, and each of these is kind of the larger set, so to speak, or like the coarser set. We'll get into this more kind of in the next lecture, and this is a big topic to learn about. This is really, we're going to eventually see this as something called a sheaf. But we won't see it for a little while because it's kind of a lot of machinery at first. And I want to give you all some examples, like some cool results of algebraic geometry and not just like a ton of machinery. But I don't want to go too lax on machinery either. So
Is there a way to represent the bracket, some other conditions, but rather than explicitly write G over H?
what do you mean?
But I didn't want to do the bit. I didn't want to write a quotient. I'm trying to generalize. So, is there like an algebraic condition that's no other ideals or anything?
I don't think so.
You don't
I don't
have to
think that-
divide by eight.
So you're like a little.
Yeah,
Yeah, it's the can.
Right, but
so if you wanna talk about just the functions where you don't divide, that's gonna be a subset of the regular function. And they're just gonna be, polynomials, in a
Yeah.
polynomial ring.
Namely, if you have something that's regular on all of X, then on any open subset, it can be rewritten as either itself, or it can be rewritten as itself times 1/1 or some other thing over itself.
I'm trying to avoid actually giving commutative algebra here, so.
Yeah, I will say if you push further on this, you're going to only really get more commutative algebra, not less. If you make a really big jump that I can talk to you about after, and if I understand a little bit more about what you're trying to use it for, maybe there's something. I don't know.
Oh, just every time I see a quotient,
Cringe a little bit.
so, I guess I was just looking for more of like an algebraic condition.
Well, actually, maybe this next concept will give you some sense of peace. So, kind of the condition that we're going to want to impose on like relating varieties to each other with morphisms is this thing called a rational map. And so the idea of a rational map is, and this is what the entire focus of next lecture will be, so don't take this too seriously. But the idea is that if we can establish some sort of correspondence between varieties such that their coordinate rings are isomorphic, then we have a relationship where like they're related. There's a function going on. If we have something that goes back and forth between them, we call it birational. And you can think of it as like two varieties are isomorphic, except at finitely many points that don't follow this condition as general translates. We'll talk about this more in depth next time. But the idea is that if you can get the coordinate rings of two varieties to be isomorphic as algebras, then you can get some sort of birationality going on.
This is like a local.
Yeah. So this is a field of algebraic geometry called birational geometry. Okay. So one final example in the last 2 minutes. That's pretty short. Just to compute one ring of regular functions for people. So the ring of regular functions on A2 minus the origin, so the affine plane minus the origin, is the same as this as taking what's called the localization at a point. So the idea is that given something like the coordinate ring, if we want to take all of the regular functions where we're not dividing by something in an ideal, right? So all of a of x except for anything with a denominator in the ideal of f, then what we're saying is we're localizing at f, or we're localizing at the point corresponding to f in affine space. So if f is the minimal polynomial of something, this corresponds to one thing on the affine line. We're localizing at that point by not dividing by anything. So it's, d over h such that h is not in f. This is called localization by an ideal. So if we want to compute the coordinate ring of the affine plane minus the origin, this looks a lot like localizing by the ideal x plus y, right? So k over x plus, or k over x comma y as a polynomial ring, mod, or not mod, localized at the ideal x plus y only vanishes at the origin. But this is kxy localized at x union kxy localized at y. Well, the localization at x is going to look like kxy 1 over x. And then this is going to look like kxy, nope, this is 1 over y. And this is 1 over x. There we go. But then their intersection is just k of xy. So in this way, this is what we would say, like the affine plane minus the origin, or minus really any point, is birational to the affine plane. This is something that we'll talk about more next week. Yeah, another way of viewing this, by the way, so like localizing is like looking at the distinguished open by f, right? It's things, it's the denominators have to come from the intersection of the coordinate ring of the distinguished open of f and the coordinate ring that you care about.
I think I'm missing something with you mentioned it earlier, so X plus Y, we're somehow recentering stuff. Maybe I'm not, this
Yeah,
doesn't vanish at just 0, but I don't understand I don't remember the statement you had earlier of a circle. Or just let shift stuff arbitrarily. Because X plus Y vanishes at a lot of other points already.
yeah,
As a polynomial, not just at 0, so that.
the idea, yeah, the idea is we're removing a point. So
But
what,
that's not the ideal that corresponds to it. X plus Y.
That vanishes at 1 negative.
oh, oops, yeah,
Stuff like that.
there we go.
We're localizing by itself, the whole thing. Then that's the ideal generator of X, Y, and that's the polynomial.
Non-constants,
Yeah,
so. I guess that makes sense.
Yeah.
You're dividing by everything that's, you can only divide by constants, so that's K join X, Y,
Yeah.
So it's just K.
so it's just.
no, it's K adjoin X, Y. Like, this is what we end up showing, right? We can only divide by things not in X, Y, so we can only divide by constants.
Oh,
Yeah, you were right, good call on the X plus Y, but yeah, the idea here is that you only want to be able to divide by KXY.
no,
Yeah, but then this ideal, the variety of the ideal, so the things vanishing on things this ideal, is exactly the origin.
trivial.
Yeah. And then if you wanted to move this to be some other point, it would be X minus A and Y minus B, you know? Yeah, and this kind of actually, this points to why affine space is boring, right? Because if you're thinking of varieties as being like irreducible, well, then the only irreducible like thing is going to be points.
Well, no, what?
No, like on the line, on the affine line.
Oh,
Yeah.
on affine, but that's also the only varieties. On the
Yeah.
affine
Yeah, exactly.
are points, and that just says the affine line isn't interesting.
Yeah.
Yeah. Because I think multivariable.
Oh yeah, multivariable gets more interesting. But yeah, in terms of like all of the easy examples that we can do with A1, it gets kind of boring quickly. Yeah. I didn't mean to say all of affine space. Yeah.
This is a general question. What are the uses of this in the real world? Like, do you use it for like computers and stuff, or do you use it for like economics, or like what can you apply this to, or is it just purely mathematics?
You can apply it to a lot of things. There's a lot of cryptography stuff that relies on this sort of stuff, but there's also a lot of physics that relies on this stuff.
It takes a while, I think, to get to the point where you can apply it to anything. But it definitely can be. Yeah, cryptography, like a lot of cryptography firms and government agencies like algebraic geometers and like commutative algebraists. That's a big thing. Mathematical physics uses a lot of algebraic geometry, and really it's kind of like a field that is tangent to a lot of other fields of math. So a lot of people will like use some algebraic geometry when they get stuck on something. Yeah, and then a lot of like pure math fields rely on it heavily for a lot of machinery. The theory of schemes turns out to be this like wildly useful thing for a lot of people. So, yeah, I'm gonna go ahead and end the recording. So,
Oh, yeah.